好的，那我们就准备开始。大家好，欢迎来到气候动力小组的周末报告会。今天我们很高兴请到了来自中科院大气物理研究所的潘宝祥研究员带来一场报告。潘老师本科毕业于武汉大学，于清华大学取得水文水资源工程硕士学位，随后于加州大学欧文分校取得气象水文博士学位，师从 Throshin 教授。随后潘老师进入劳伦斯·迪弗摩尔国家实验室进行博士后研究，对融雪预测、数据驱动气候模式参数化等进行了一系列的工作。之后继续留在该实验室担任研究员，研究方向为利用机器学习改进动力气候预测，通过融合数据模型来增进气候变化适应等。潘老师于今夏开始在中科院大气物理研究所与上海气质研究院担任研究员的职务。继续从事深度学习动力气候模式方面的工作。今天呢，潘老师将为我们分享他们关于利用深度学习来改进气候预报的工作。非常期待今天的报告。大家如果在报告中有需要澄清的问题，可以在对话框中留言，或者直接开麦提问。其他的问题我们可以留到最后进行集中讨论。接下来我就把时间交给潘老师，请他来为我们开讲。
好的，谢谢文达。我这次报告因为有一些其他的同事要听，所以我就用英文来讲。然后我回来也有一段时间了，可能英文不是很顺畅，或者是说大家如果是有一些需要 clarify 的东西，可能直接告诉我就好，然后我们可以中途打断，我们进行来讨论。So today I'm going to talk about how we can use deep generative model for probabilistic forecast. What I will cover in this talk is the following things. First, I want to introduce a mindset of using probabilistic modeling for climate studies, especially for probabilistic forecast. And I want to introduce you a bunch of tools you might have been familiar with, or it might be new to you. It's called deep neural network. And I want to cover something called like convolutional neural networks, which you must have known it. And then we go from pure supervised learning to some generative models like variational autoencoders and generative adversarial net. And also in the very end of this talk, I will talk about the denoising diffusion probabilistic model, which I think should be a game changer for all fields that try to use deep learning. And I will give an example of data-driven global seasonal forecast and compare it with dynamical forecast to highlight how we can use deep learning to enhance our process understanding. And also I want, based on this example, I want to illustrate the pipeline of how we use deep neural networks to do research in the climate community. And finally, I want to give a very brief outlook about how the field could evolve in the future. Especially, I want to talk about a direction that we can use machine learning to summarize the very large amount of data in coupled model in the comparison project to illustrate many of the problems that we want to know about the climate system. So let's start from a history review of this field. The history of observing, modeling, and predicting the climate system dates back to the middle of the 19th century. We will start to use electric telegraph to collect the weather data. And based on that, we can extrapolate the weather charts to make some very empirical weather predictions. And once we have this evidence, we know that we should have some theory. So Birknis developed the primitive equations that govern the atmospheric dynamics. And once we get the equation, we want to solve the equation. And we know that Richardson tried to solve it by hand, but he did not make it. And in 1945, this inspired von Neumann to apply the first numerical computer to do the automatic numerical weather forecast. And thereafter, we have Giuliani, who developed a report summarizing what this field could go in the coming 70 years. Until now, we have the so-called global climate observing predicting system, which is based on the observation network consisting of the ground-based observers and the remote sensing observers. And also we have the process-based models, which may range a large spectrum of complexity from the like just atmospheric only models or the models that built around the atmosphere and the ocean. And there are three landmarks that we should care about. The first one is that is in 1906, as I mentioned before, like physical laws of the whole geophysical fluid and large part of other processes are completely known. I know someone may not agree with me, but I think that the whole of geophysical fluid dynamics has been known, and the other parts, they are partially known. However, the resulting equations are too complicated to solve. So this is the first landmark. And the second landmark is that in 1945, numerical approximation of these laws become feasible, yielding modern weather climate prediction. Yet we have large forecast errors. They arise from initialization error, model bias, and sampling bias. By sampling bias, I mean that this is a chaotic system, and starting from an initial state with very small error in estimating the state, we may result in very distinct trajectories. And the third landmark is in 2007. Climate models start to be used as economic models to balance the prosperity today and sustainability tomorrow, which means that we think we have a coupled model that can predict the whole climate system. And we use this system to predict what the external forcing we give to this climate system will result in different future climate scenarios. And we believe that if we want to have a prosperous tomorrow, we should like lower our expectation for today. Yet, many people do not really trust climate models because their fidelity are hampered by the model bias. We know we don't have a perfect model. We don't know exactly what happens in the land, in the cryosphere, in the biosphere, and we can partially resolve the geophysical fluid dynamics. And second, even if it's a perfect model, starting from an initial state, we know that we have a large internal variability noise. And third, we do not sample all the possible scenarios. The scenarios we sample nowadays in the SEMI project is already simplified and too few. So these are the three landmarks. And like roughly, we just follow Zhu Chinese picture of what this field will evolve. And what we do today is like we try to refine Zhu Chinese picture by clarifying the following three uncertainties at specific scales. The first one is the internal variability noise, and the second is external forcing. The third is model formulation deficiency. To illustrate this point, we may consider the weather forecast. First, how are these three uncertainties manifest themselves in the weather forecast scenario? First, we use observations to partially control the internal variability noise, which means that we have an understanding of the climatology for yesterday if we do not have any observation. But once we observe the climate system, we can shrink this uncertainty to this initial state. And how can we know the model formulation deficiency? Well, we use a lot of hindcast or reforecast to identify and reduce the model's bias. And we know that at weather scale, the external forcing might not be so important. And at sub-seasonal to seasonal scale, we also use observations to partially control the internal variability noise. And we know that the initial state uncertainty will grow into a large distinct clusters. So we use ensemble, dynamic forecast ensemble to estimate the remaining impact of the internal variability noise. And we use hindcast to identify and reduce model bias. But we know that now the discrepancy between the forecast and observation results from the combination of internal variability noise and model formulation deficiency. Also in sub-seasonal seasonal forecast, there is a very important concept called the opportunity of predictability, which means that if we just look at the atmosphere, some external forcing from the ocean or from the stratosphere, they may impact the predictability, how this uncertainty evolve. So it's a combination of these three. And climate change detection attribution, we try to sample initial state to estimate the internal variability noise. And we use control experiments to identify the impact of external forcings, which means that we set different scenarios, and under these scenarios, we run our models So the difference between these models might reflect partially reflect the difference between the external forcings. And how can we know where model is biased? Well, we don't know, but we use multi-model comparison to see if they do agree. If they agree, we may have a larger confidence of if the model is correct or not. And finally, everything is based on dynamical models. So we have the model diagnosis and development, and we are using weather hindcast to identify the fast-growing component of model errors. And we are using climate hindcast, like we run the model for 150 years, and we see how the model's climatology different from the real-world climatology. By climatology, usually it means that the mean and the variance, usually the first order and second order of the climate. But it's very unfortunate that as model and data complexity grows, the progress usually slows down. This is ubiquitous in a lot of fields, like the iterative research cycle, where we try to identify where some theory is wrong. We come up with hypotheses, we design the experiment, we collect the data, and we get the result. We go back to our hypothesis. This is called iterative research cycle. So this is the iterative research cycle is usually a decelerating cycle, which means that the first comer, they find the most important hypothesis, they develop the fundamental theory, and the second comer, a second important theory, and the last comer, he refine the details. And many of us are refining the details proposed by Zhu Changyi 70 years ago. But this will not be consistent, because sometimes we have something called paradigm shift. And someone believes that we are having a paradigm shift in climate science. So this is the hope or hype of deep learning. And we know that deep learning is some data-driven technique that utilize big data, big computation to do some learning task, which means that an algorithm, once you design its objective function, given a lot of data, given a lot of computation, you can improve the model's performance with regard to the objective function that you design. And many people have picked up the two, like in the past 5 or 8 years. And here is a categorization of supervised deep learning application in climate science. Usually it's about supervised learning. The first is to learn to infer parameters by accelerating model inversing. And this is represented by the work from Tapio Schnedt in the GIL paper called Earth System Modeling 2.0. And the second is to go a little bit further, is to learn to represent unresolved processes, or usually we call parameterization, from high fidelity data set, like observations and high resolution simulations. As once you learn this relationship, you replace the cost model of parameterization with the learned model and try to run the model for a long time. But there are a lot of mistakes in this practice, which I will highlight later. And this is a paper from Stephen Ross, learning convection parameterization from super resolution models. And the third one is to go even further, is to learn analog forecast from observations and simulations. And you can see Jonathan Wynn's paper and Yogi Ham's ENSO prediction, 2-year ENSO prediction paper. And finally is to explore foresight from data, like trying to go from machine learning to artificial intelligence to find foresight or insight. I highly recommend these two papers. These are the papers that inspired me to go deeper, like from pure supervised signal to generative signal to model both signal and noise in different scenarios. This SAPS paper, climate change detectable in 1 day, you may find it ridiculous, but once you read the paper, you will be astonished. And the other is Libby's paper, viewing forced climate pattern via an AI lens. These are really good papers. But to learn this task, usually we should have is to do supervised learning. We should have sufficient high quality paired observation simulation data. Usually is trying to channel the data from different sources and find their connection in order to reveal the deficiency from each side. So this is usually difficult, if not impossible, given that we only have short range incomprehensive observations. And usually the problem we care about is of high dimension. And finally, the climate dynamics is chaotic, which means that we need a very large effort to control the chaoticity to provide us with this high quality paired data. and I don't think it will go long. So I know some of us may not be familiar with machine learning or supervised learning. I will give a very intuitive example here. It's about estimating precipitation using the resolved dynamics. We know that in climate models, a very important deficiency is that we cannot make good prediction of precipitation. And actually, since the dawn of modern climate science, we know that the precipitation pattern is dominated by the circulation pattern. And here is the Bergen school cyclone model. And once we have the convolutional neural network, which is quite suited for imagery data, and we know that we can use the resolved dynamics like the geopotential height, the wind speed, and the humidity to estimate the precipitation here. And we collected all the reanalysis circulation data, and we collected the gauge-based observational data. And we know that it has special pattern, it has temporal consistency. So we try to use some useful inductive bias. It's a very important concept in deep learning, inductive bias. It helps us to reduce overfitting. And what OK 了吗 ？OK， so the very simple example is that we can use some phenomenological understanding of the connection between the circulation and precipitation to estimate precipitation, and there are some unique things about climate data. That is, we have different sources, and the gauge-based data, gauge-based precipitation usually is the most accurate, but we do not have uniform observation, so we develop some mask to mask out the unobserved data points. And what the result look like? It's like this. So we can remove the mask, and try to see how the model works in some unobserved regions. And here is那我们就接着开始讲。那我们就接着开始讲，好吧？可以听到是吧？
可以，没问题。
哦，好的。So we have the good cheating skill of convolutional neural network, and this is what people usually do like 3 or 4 years ago. We have some pair data of reanalysis data and observation, and we know that in reanalysis we don't have good precipitation observation. So we try to relate the good the reanalysis circulation data, which we can trust, to the to the precipitation data which we observe. But we have high cheating good skill. If you look at this hurricane event, we know that we could not have this. We underestimate the extremes, like in the hurricane I, and with the spatial diversity is not so good, and we overestimate a lot of results, and the temporal consistency is not as good as we have expected. And the implication is that we should move beyond the conventional skill matrix, and this I think this is what the DeepMind's Nature paper did in precipitation nowcasting. I think that can be used for precipitation downscaling if you include the adversarial loss there. You can have a discriminator, which is another neural network trying to tell if it's from observation or simulation, and it can like go beyond the conventional skill metric. And also you can learn parameterization probabilistically, which I think is more promising. So what I learned from this lesson is that by bridging reanalysis data and observational data using DeepNet, we really get we can get the evidence that precipitation can have better determined precipitation estimation. Sorry for the typo here, but we have some really big mistakes that we should overcome. The first is that we fail to model the subgrid scale process uncertainty. And we fail to model the growth of subgrid scale process uncertainties. We fail to account for the uncertainties in the reanalysis and observations. We know that the supervision data, they are not perfect. And finally, we need costly control experiments to prepare the supervised training data. And even if we have done that, as I mentioned earlier, for example, we train some like convection parameterization using deep neural network, and we try to attach it to the original cost resolution model. But we know that we are building a black box model like that links x to y, fx equals to y. But the x in training and in employing is totally different, because in training we are trying to like collect the constant high resolution simulation, but in using the model, we're just using the original cost resolution model. There is something called distribution shift in the input part of this black box model, which as we do iterative computing, we know that, well, it might explode. And this is the instability issue in computation. So that's why I think if we stick to supervised learning, what we can do is usually we try to come up with better deep neural network models. We are not coming up with new models. We are trying to borrow from the computer science community. Let's say if we can go from convolutional neural network to capsule, to transformer, to twin transformer, to graph neural network. But we cannot overcome these issues. The reason is that we do not have a good understanding of where the uncertainty is and how can we categorize different sources of uncertainties. So if we stick to the supervised learning mindset, there is no hope. But do we have some hope somewhere else? And I will provide an example of a conditional generative model for global seasonal forecast as a case example to show that if we carefully take care of different sources of uncertainties, like the uncertainty from the observation, uncertainty from the reanalysis, uncertainty from the growth of initial state uncertainty estimations. If we carefully look at all these uncertainties and build them into a same model, we may overcome these issues, and we may overcome the effort, and we may just don't need the effort to prepare such large amount of supervised training data. And I think that's where the hope lies. So let's look at the seasonal forecast. And we know that seasonal forecast is pretty important for a lot of sectors like the agriculture, economy, finance. And mostly in today's seasonal forecast, we rely on the global seasonal forecast system, which consists of the observations and the dynamical forecast models. But there are some, how can we do seasonal forecast? The first question that we ask is, how can we do seasonal forecast? We know that there is a predictability limit of weather forecast. We cannot make deterministic forecast up to 2 weeks. But we have some key prediction sources, like from the slowly evolving component, from the sea surface temperature, sea ice, volcano. And we know that they provide some low frequency signal constraints on the atmospheric dynamics that can help us make like extended range forecast from sub-seasonal scale up to decadal scale. And the impact of the prediction source, they may have some impact on the predictor that we care about. So there are some local connection, there are some tele connection. Nowadays, there are a lot of papers talking about how X, the predictor, Y, the predictant, the thing that we want to predict, and the probabilistic relationship between Y and X, which is represented by a conditional distribution here. Py given X varies in a changing climate. How external forcing influence the connection between the predictors and predictant. And it's very important, but usually we cannot do it because we don't have a lot of sampling about the what a changing climate is. And we cannot afford large ensemble forecast of different X. We have a large variation of X, like different Ensel types, different tidy connection patterns, like the connection here, and how different Ys we care about. And usually it's a very large dimensional space. So we need to run maybe hundreds, tens of thousands of samples to determine Py given X. And what prevents us from having perfect seasonal forecast? There are three reasons if you look at this paradigm. First, we do not have a good initialization, which means that we may start from a wrong place. We don't have enough observations to constrain our initial state. And there's something called state shock, which means that once we constrain the model world, the model state in the model world with observations from the real world, we may quickly drift away from this constraint because model has its own climatology. And we do not have a systematical way to deal with this state shock problem. And this problem is highly related to the problem of warming up in climate modeling. Warming up, we run the model from some initial state, we run it for tens of thousands of years, and then we start from there to do the simulation. Why do we need to run tens of thousands of years to warm up the model? What do we mean by warming up? We don't have a good definition of warm up and state shock. But if we look at the such literature from statistical physics and from like the probabilistic machine learning, we know how to define them, how to tackle these problems. So this is the first problem, poor initialization. And the second problem is poor model. The model usually has really low resolution, like 2 degree, 1 degree. And there are some parameterization errors from almost everywhere. So this will drift this trajectory from the proper position to some position that we don't want there to go. And finally, we have insufficient sampling forecast spread. Here is like 10 to the 7th grade, 10 to the 8th grade for the ocean. But usually we only have like 10 ensemble members to sample what is possible in one season ahead. So these are the three barriers. And how do we do seasonal forecast nowadays? We already have two methodologies. One is called dynamical forecast, which is the mainstream here. And the other thing is called empirical seasonal forecast. And I know that I think there is a timeline here. It's called the rise, the fall, and the re-rise of empirical seasonal forecast. The first rise from the first globalization, where Gilbert Walker find that there is a worker circulation, and Jacob Bieknis find Ensel, and Klaus Hasselmann said that we can treat the atmosphere and as the noise, and the ocean as the signal, or both of them as the noise, and the external forcing as the signal, and use some signal processing techniques to understand the climate system. So this is the first rise. But as we have developed the theory and developed the computation facilities, we know that we should have a ground-based dynamical forecast paradigm. That is, we start from an initial state, we iteratively computing the evolution of the atmosphere, the ocean, land, cryptosphere, biosphere. And we have the general circulation model or global climate model from Giuliani, from Philip, and Tusuki Monabi. And but unfortunately, given these deficiencies, we know that this progress is slowing down because everything is getting more and more complicated. So how can we remedy this? There is a possible renaissance. That is, we may search from the large amount of climate simulation data and find where the initial state matches observations and see, like if from climate simulations, they may evolve into certain state, and we use this data as our prediction. So this is the so-called, it's a nearest neighbor method. Like we search from semi-5 simulation and find where it matches reality, and the next year it will match reality as well. And we can go a little bit further, like using deep neural network for multi-year Ensel forecasts. But there are some deficiencies here. But let's first talk about their implications. So general circulation model, this model, they obtain their seasonal forecast skill from key prediction sources. Like if you look at ocean, it dominates the atmospheric variability for the coming year. And machine learning can summarize how key prediction sources modulate seasonal variability in GCM simulations. It's called analog forecast or phenomenological forecast. But there are some deficiencies. First is that we only care about limited regions or specific climate phenomenon. We don't care about a lot of new things, like can we do globally? Can we do it globally? Can we just predict different types of answer? And second, it does not rigorously represent different kinds of uncertainties, as we clarified here. 3 uncertainties: initialization, model formulation bias, and the sampling of internal variability noise. And third, if we cannot represent these uncertainties, these endeavors, they do not provide rigorous suggestions for conquering the forecast barriers. In the very end, we want white box models, which means everything here is clear and the uncertainty here is clear. So we can like truly trust our model to do some planning, to do some adaptation for future risks, and to make some finance investment. So these are the 3 limitations. At this end, this is not the end. So we can use a deep neural network, a generative model, rather than fx equal y, a supervised learning model, to model these 3 uncertainties and to link this empirical forecast with dynamical forecast. And by comparing these two, we finally know where the model is wrong and how to improve the model. So deep learning is used to provide foresight of where model is wrong. So the most important part in doing deep learning based climate problems is to formulate the problem. How this problem is formulated is of vital importance. If the problem is formulated wrong, even if you have a lot of data, a lot of computation, the results are not trustworthy and they provide nothing. So how we formulate this problem? We know that there is the internal variability noise, so which resides in the probabilistic connection between x and y. So we know that x does not deterministically give us a singular y. And we know that at different models, the probabilistic connection between x and y, they are different. So the uncertainty of py given x in a single model is called aleatoric uncertainty in the climate community. And the uncertainty due to our imperfect understanding, due to the imperfect deployment of a model trained in one domain applied to another domain, usually we call it epistemic uncertainty. So it is here in the conditional part. So what we are trying to do is that we want to model py given x and m. If you consider it in the seasonal forecast context, y is global precipitation or temperature anomaly in the coming season. X is the ocean heat content, how the ocean thermal state at the current in the current day, and M is different models. We don't have a lot of the observations. If we have million years of observations, we don't need M here. We just use the observational data to build py given x. But since we do not have observational data, we have to go to synthetic data, which comes from climate models. So different models may have its own opinion about the relationship between y and x. That's why we formulate it as a generative modeling problem of estimating py given x and m. But here we have several challenges. So how can we model high dimensional conditional distribution? How to handle data inhomogeneity? So we know that for different m, the relationship are different. So how can we do that? How do we handle high dimensional spatial spherical data? So these are spherical data and these are high dimension. So we provide 3 solutions. The first thing is how to estimate high dimensional conditional distribution. We use variational autoencoder, or so-called stochastic gradient variational base. And how to handle data inhomogeneity? We use some techniques from transfer learning called entity embedding. We embed different GCMs into a latent space. It's like a metaverse of GCMs. We really want a metaverse for GCMs because it's a metaverse. The world we live in is a universe. The world that CMIP resides is a metaverse of different GCMs. And we want to know the connection between different versions of the GCM. So we use the entity embedding technique. It's not the optimal, which we will come to later. And third, how to handle the high dimensional spatial spherical data. We use some so-called conv-deconv net for plenary data. but this is not optimal as well. We should use spherical convolution. And let me explain briefly about this technique. VAE, variational autoencoder of stochastic gradient variational base, is to estimate a high dimensional distribution, which is here, using some like variational technique. So how can we do that? We can easily sample a uniform distribution here, and if we can build a bijection between these two spaces, then we can easily sample from here and put it into some functional transformation to get here. And to estimate this, we need to derive these equations, so-called the evidence lower bound equation. We're trying to maximize the likelihood of the model that can give rise to our data from different models. And we know that this is computationally intractable, which means that for each y here, you need to consider every possibility here to get this point. But we know that if you search from a high dimensional space, you integrate this, it requires forever to compute. So what we do is that for each point here, we come up with a smaller space to know where this sample might come from. And for each sample here, it might go directly yield some sample that is realistic. So that's where this equation comes from. Unfortunately, we have an analytical form for this evidence lower bound. This allows us to use our favorite machine learning technique called stochastic gradient descent to maximize this term. And you maximize this term, and we know that the phi does not depend on here. So this one will be minimized. And as we minimize this one, we know that each point here can find a proper possible latent that represents this one. And then this thing will be pushed up implicitly. So this is the basic thing about variational autoencoder. It has little thing to do with the so-called autoencoder thing. And this is how we sample how can we estimate the high dimensional conditional distribution. And how can we handle the data inhomogeneity? Well, we know that there are some similarity and difference between among GCMs regarding how they represent different aspects of the climate system. So can we learn to represent objects as continuous vectors? I know that many of you might have noticed these figures. So this is how we represent the world using vectors, using dense vectors. Like if we have vector for man and king and queen and women, and we can just do some subtraction and find the vector for different other vectors. And the task of natural language processing is to find a proper dense vector for different words here. And here, if we want to look at the specific relationship between X and Y in different GCMs, we can employ a very similar technique to denote different GCMs as a dense vector. And I will skip the conv and deconv part because it's fairly familiar to you guys. So we train this model using all the semi-5 and semi-6 data, which sums like to almost 0.2 million years of data. And we use different scenarios, which is also some deficiency of this work because we should clarify which simulation comes from which scenario so that we know that as the external force changes, how predictability will change. And many people are doing this kind of work, like how P, Y, and X change in a different climatology. Like will the weather forecast become more accurate in a warmer climate? Or will seasonal forecast become easier in a warmer climate? And we don't have a very strong evidence from some big data analysis. I think that if we can categorize different scenarios, we may have a better answer. And here is comparing our result with the dynamical forecast from the same model. We developed this so-called conditional generative forecasting model, which is estimate P, Y giving X and M. And now let's specify which M we are using. We are using the Canadian model, and we are using the model's input vector to predict the possible outcome of next season climate. And here is the correlation coefficient. And we know that it's pretty okay. And we can also apply the same model to the real world, which means that we force the trained model using observed ocean heat content and predict next season's precipitation. And we can also compare the results that we use the same model for real world forecast. And the very important finding here is that they achieve similar pattern. But here, if we use this model, if we learn the seasonal predictability information from this model, and we may even achieve better results than directly deploying this model in real world forecast. This is a little bit unbelievable because we are using the same model and this model is highly simplified. How can it achieve better results compared to this one? And here we are using like 1,000 ensemble members. And we sample from this latent space. And here it's using 10 ensemble members. So we assume that the difference might come from the fact that we are not using enough ensemble members in this model. We will come to this hypothesis later. And here is how can we use this deep learning technique to compose some multi-model ensemble forecast. So how do we do that? We sample from each model, like Px given y and m. M ranges from m1 to mn, and we compose this ensemble. And also we may search from we use some observational data to do a slight fine-tuning of models latent space to see that where the real world entity embedding vector for the real world climate resides in the model world and entity embedding vectors. We will come to it later. And here is the NMME multi-model ensemble forecasting results. And here is for temperature, a very astonishing result for here is that this is how we use the trained model for model world forecast. So like Px given y, how Py given how the ocean heat content influence the next season's temperature or precipitation. And we know, and it's interesting that in the model world, seasonal forecast is a very easy task here, as we can achieve a correlation coefficient above 0.8 for most regions. But if we apply this relationship for real world forecast, it quickly decreases. But it's still a little bit better than the dynamical seasonal forecast itself. And interestingly, this thing also happens for the ensemble forecast scenario. So let's come to the original hypothesis that why this one works better than this one, and this one works better than this one. We assume that it's because of the ensemble size. And if we here is if we just look at this one, the global average correlation coefficient scale of the forecasting models using different forecast ensemble member. So here is the green is this model here. The conditional generative forecasting model using this specific GCM, and the red is using is the dynamical forecast using this specific GCM. We start from the observation, we run the model. This is red, and the green is that we learn from its long-term simulation, try to find how the X influences our Y, and then we deploy this model for real-world forecast. And here is the ensemble size. So we notice that as we increase the ensemble size, the model's average correlation coefficients, they grow and following a similar trajectory. But as we exceed 8, we do not have a dynamical forecast because it's just too costly. But we can keep sampling from this conditional generative forecast model, and we achieve a consistent improvement of forecasting skill here, which confirms the hypothesis that the current dynamical system failed to fully deploy the predictability capability of this model because it has too few ensemble members. Notice a question here.
Yeah, there is a question from Professor Gang Chen. Please.
Okay. Yeah, okay. Sure.
So I think, yeah, I'm just curious about how you did it. So, because you have some data used to train the model, you also have data used to make forecasts. They are presumably different, right?
Oh, yeah. I think I failed to clarify this point. So in seasonal forecast, what we did is that we assume that the sea surface temperature has influence on the next season's like precipitation. Let's give an example. And when we do dynamical forecast, what we did is that we collect all the observational data to estimate X. And then we run the model here. And we run it for 1 year. And we get all the different ensembles and we collect them, we compare with the real world trajectory to estimate the model's capability. And if we want to just use the model for next year's forecast, we collect the data here and we run the model and we wait. This is the dynamical forecast system I think every one of us should be familiar with. So what we did here is that we have the CMIP long-term simulation. And so we collect the previous season's sea surface temperature and the next season's precipitation for all the simulation years. So which gives us this long-term, this training data. So we have this year's sea surface temperature, next season's precipitation, next year's sea surface temperature, next season's precipitation. So chop out the slices of sea surface temperature and precipitation from the long-term simulations.
So are you talking about historic simulation or pre-industrial simulation?
All of them here. I'm using all of them for now, but I don't think it's optimal. I think we should represent each scenario separately using some transfer learning technique and say that.
I'm just curious how you did it, sorry. So just clarify, so you are using pre-industrial simulation and historic simulation to train your model? And when you try to evaluate your model, are you using historic simulation or forecast simulation? I'm just trying to figure out what data you are using.
Okay, I use all the CMIP 5 and 6 data that I can get from Lawrence Livermore Lab. But I exclude the year from 1970 to 2010 from historical simulation because I don't want to overfit.
Sure.
And for all the rest data, I train a model for PY given X and M. And you get this relationship of PY given X and M for different models, for different scenarios. Like for CMIP 5, CMIP 6 deck here, for future scenarios here, you get this relationship and you test it for 1970 to 2010 in the model world. The model during training has never seen the data here. And then you get the estimated distribution of Y, and you compare this Y with the model simulated Y, which give you these figures. Okay. And you can also apply this relationship for real world forecast from 1970 to 2010. And you compare with observed precipitation, and you get this correlation map.
Okay, so when you say neural network, the parameter of the network are the same for all of the data you have. So you can use the same, you can use what you learn and to do, same. Okay.
Yeah, and this model can be used for global seasonal forecast now. Okay. If we get the input data.
So for the one you have in the top row, you say like the forecast based on CAN, ESM, and also CAN and CM4 forecast. So are they based on the same data set, or is the one you have CGF based on all the data you just described?
So CGF is based on all the data that I described, but it's customized for this CAN ESM in this environment. Okay. Because we can keep the M here, keep M to CAN ESM, and we sample the PY given X in this model.
Okay, but you also learn things from other models, so that's why your forecast is better.
Yeah, you also learn from other models, and we don't think that's the reason that makes this model better. Because
I see.
We don't think that's the only reason, because this model can give us large ensemble size. So that's why we deploy this experiment So if we just use one ensemble member, the performance is not as good as the dynamical forecast. If we look at global, tropical, southern, and northern mid-latitude. But as we increase the ensemble size, which means that we better sample the internal variability noise, we may have better estimate of the mean prediction, which give us better correlation coefficient.
Okay, so yeah, I'm just trying to understand what you have. So basically, you can generate noise or signal based on training of the model, and as you increase the ensemble size of your static model, and you can make better prediction.
Yeah, it's okay. Not we are trying to model both the signal and the noise by modeling the conditional distribution. You can once you get the conditional distribution, you can get the mean of the prediction. You can get the expectation of py given x. You can also get the variance of py given x, and you can also get how the variance, the p variance of py given x changes with x. That's how predictability changes with initial state, and that's in the coming slides.
Okay, just one more clarification question. So you said like you are interested in the probability change over time. So for different scenario, do you also have a different partial, like the when you
not
learn?
Yet.
Not yet.
Not yet.
Okay.
We at the very beginning, because it's worked from 2 years ago, we just mix all this data. If I do it today, I will just embed different scenarios. So for example, there's a question: would the weather become more predictable in a warmer climate? Or do we have higher predictability in pre-industrial times? We don't know that. But if we can embed this one, and if the model is powerful enough to encode this into our model, we may have the answer.
Okay, that's so fine. Thank you very much. Yeah, I think it's very interesting. I probably should let you continue. I just wanted to ask some clarification question.
Yeah, I think it's very necessary to clarify this because it's a kind of complicated, and this paper got rejected 3 times because we are using something that they don't appreciate. They say that we are doing machine learning, but we have never seen this kind of work before, and they don't know what we are talking about. I know that it's pretty difficult to clarify, but I think it can bridge empirical forecast and dynamical forecast and provide foresight for both sides. Okay.
Excuse me. Excuse me. Someone asked, can you use your laser pointer for the presentation? So currently we can see, but
I'm sorry, I don't have that, but I will. Is there
we can still see
annotation, right?
Yeah, I mean,
annotation. There's an annotation, right? Let's see.
There is a
both sides. Format.
Yeah, we can see the all right. I think
Okay. So let's continue. Okay. Can remove this one. And okay. So we know that we are trying to represent the relationship between the py given x for different models, and we are doing some embedding for different GCMs. And here we're trying to reveal the deficiency of how different GCMs represents the relationship we care about using some latent space modeling technique. So the entity embedding, I call this the metaverse of the GCMs, because we are trying to see that for different GCMs, how they represent py given x. And once we get this vector representation of these GCMs, we can plot them in a 2D or 3D map using some dimension reduction technique. And also we can try to plug in the observational data and have an estimate of the model's latent, of the real world latent space, which is labeled as M here. And here is for the for precipitation. Here is for temperature. The red is for 75 GCMs and the blue is for 76 GCMs. And we noticed that for precipitation, almost all models, they are not so close to reality except these two things, except these two. And this suggests that these two models might be really close to reality regarding how we represent the relationship between sea surface temperature and precipitation. So this suggests that these two models might be good. And for the temperature part, we know that most models can do relatively okay, as they are all surrounded by the reality is centered in this GCM metaverse. And by this, I think we may have the potential to reveal how different models they differ regarding certain aspects. Previously, we were just seeing, well, this GCM differs from reality regarding the mean temperature, the mean precipitation, the mean or the variance of precipitation, variance of temperature, like we are seeing the variables. But here, using this technique, we are seeing how different GCMs differ in their functional relationship. We use deep neural network to extract the probabilistic function in these GCMs and see how different GCMs differ in this aspect. And then we know that many people care about the explainability of these black box models. And let's see a case example of the worker circulation. We look at the precipitation in maritime continent, and we plot the gradient of how the change of ocean heat content, the potential temperature of the ocean layers, in Nino, in La Nina, how they modulate the precipitation here. And if it's red, it means that it's positively correlated. And if it's blue, it means that it's negatively correlated. And in this field, we clearly see the pattern of worker circulation and how the evolution of, we hope to see how evolution of ENSO change this tidy connection pattern, but we do not dig deeper into it. And it's labeled gray because we do not have a detailed discussion about this part. And the third is about the predictability part, which is how the variance of the forecast model ensemble changes with how they changes with different initial state. I don't think it's a very comprehensive analysis. We just included this from our published paper, but you can see it in our archive paper. So it's calculating the correlation between the variance and the Nino 3-4, the single model variance. So how ENSO modulates the forecast ensemble spread. And here is our model. And we see similar patterns here. And this pattern coincides with how ENSO represents the precipitation magnitude. Unfortunately, we do not have an in-depth discussion about this part, but we may come to it in the later discussion part. So there we can have a comparison between the dynamical forecast and this new empirical forecast. We avoid initialization shock by learning from an interrupted round of GCM simulations. We combine the power of multi-GCMs by learning from their ensembles, and we can efficiently do large ensemble forecast. But the concept is that we exacerbate initialization uncertainty because we only consider the ocean heat content here, and we do not consider other things like stratosphere. And we inherit the original GCM bias while introduce extra bias in building the statistical model. And maybe we do not have the perfect model to build to estimate Py given X and M. It's difficult to approximate this high dimensional distribution. So this work was done like 2 or 3 years ago, and as I mentioned, it got rejected 3 times. But there is also, we are very optimistic about the result here. But there are some guys saying that, well, here you are just doing the seasonal, you are just predicting the next season's mean precipitation or temperature. And we very often we need to know some more detailed information like extremes, like the compound impact. Can we scale up this method like to really match dynamical forecast? I mean, to provide day by day or even hour by hour prediction or probabilistic prediction. At that point, I think it's like over requiring, but later we find that it's actually possible. And here I will provide two extra solutions. Well, the first is so-called GAN solution, the generative adversarial net solution. And the other is called the diffusion solution, which I'm working on right now. I will just quickly explain what it is. But let's first look at the GAN solution. A very interesting phenomenon in the deep learning community is that it evolves so fast. It's a technical revolution, I guarantee. And in the year 2014 to 2022 to this year, many people are saying that I'm doing novel machine learning research using GANs. Yang Goodfellow invented this technique like 8 years ago. But since June of this year, people in the deep learning community, they already say, why do we still care about GANs? It's because we have some really new technique that can beat GANs and overcome its defects. But here I will illustrate why we should still care about GANs. So as I mentioned in the very beginning, we know that we already care about the climate system is a chaotic system, which means that the physical laws that we have will only have partial control of reality. It cannot guarantee a full control of what the world will evolve. And in the future, we may still face with this dilemma. So how can we guarantee that we have a good climate prediction model, climate forecast model? And Tim Palmer brought forward a very interesting idea called climatic Turing test, which is to distinguish samples from climate observation and climate simulations. And it's very easy to train a human being or deep neural network to distinguish observation and simulations, like in historical climate and historical climate simulations. And here we are trying to judge their performance using the confusion matrix here. And if we look at the precipitation map in observations and in simulations, we know that due to the fact that the circulation pattern is different, the precipitation pattern is different. But even regardless of the circulation pattern, we human beings can still very well distinguish whether it's observation or it's simulation, because here it has too many results and do not reflect the terrain effect. But we can do similar thing using a deep neural network, and the accuracy is much higher than a human being. And that's what's called climatic Turing test. This is a toy model as developed by Tim Palmer in his 2014 paper. But can we just go a little bit further? So we know that it's fake, it's model. All models are wrong, some are useful. But books does not tell us when a model becomes useful. When does a model become useful? A model becomes useful if it can serve as a latent for some aspect of reality. And here we are trying to get the GCM as the latent of a generative adversarial net, where we can random sample a snapshot of a simulation or a sequence of snapshots of the simulations, and we random sample some observations, and we ask another neural network whether it's true or fake. If it's fake, what makes it fake? And can we bias correct this fake while maintaining all the physical consistency that we know? So how does this fit to the general picture of disentangling the internal variability noise, model formulation bias, and external forcing? So first, we use model as latent of reality. And second, we try to exclude the impact of external forcing here using historical simulation and historical observation from a very small time window, and exclude the impact of seasonality. Also, we try to exclude the impact of internal variability noise using some random sampling technique here. So if it's randomly sampled, they too differ in their circulation pattern, differ in their internal variability noise. So if this one cannot distinguish these two using some circulation pattern information, it must seek from other evidences, which is the physics. And then we can learn to correct the model formulation bias or correct the model parameterization bias by making simulation and observation indistinguishable. But at the very last, we know that if we cannot just, the discriminator has no physical knowledge, but we can have some physical constraints here and here to make it physically sound while still having us match the climatology here and here. And this is how it's done. I'll quickly skip this. You can search the paper. And here are some results. Let's first look at the Turing test. Here is observation. Here is simulation. Here is a bias-corrected simulation. And if we have a human being to do the Turing test before and after bias correction, we know that he can no longer distinguish whether it's from simulation or observation. And deep neural network cannot do it either because we are training it to make it less distinguishable in using this discriminator neural network. So I know that you might not be really interested in this climatic Turing test idea, but let's look at two conventional tests that we usually use to decide if a model is good or not. The first is if a model can reproduce the historical climatology. And here we are not seeing where the model is wrong. We're just seeing a neural network to tell if it's from reality or from the simulation. So we can test almost anything that we can come up with to distinguish if a model is good or not. And here are the examples. For precipitation, we test the average intensity, the extremes, and the seasonality. This is the original simulation. This is a bias-corrected one. As we can see that it's hardly distinguishable if we look at these statistics. So we have a better climatology using this bias correction technique. And the last and the most strict test is to test if it can do better weather and extended range forecasts. And here is the original CFS forecast. And here is using our model to bias correct it in a totally unsupervised way. And this is the correlation coefficient for the past 20 years hindcast. And here is the second week forecast. As we can see that we can make better forecasts. And if we attach them with a downscaling model, we can even have better high resolution predictions. And the thing asked is that we are using a deepfake technique. Is it real life or is it just fantasy? So we are using Turing test as a skill metric. And a good skill metric should inform where the model is wrong and where correct answer is. So how climatic Turing test inform where the model is biased? It's because the theory of concentration measure. If you look at high dimensional things, it's easy to distinguish if a sample comes from a distribution. So the higher the dimension is, the easier the distinguish task is. And with this, we can see that Turing test must be a very difficult test for a model to pass. And why climatic Turing test leads us to correct model bias? It's because if we are using this technique to train the model. Am I Jove?
I think we can still hear you, but we couldn't see your slide anymore.
Okay.
Can you share your slide? Oh, your reshare.
One moment. Is it? Is it?
Yeah, now I can see it.
Okay. So it's the reason why Turing test is important is because by doing this adversarial learning, we are trying to match the distribution here and here. And the distribution is of really high dimension. And if we can have the state space of two dynamical systems to match exactly, mathematically, these two dynamical systems are the same. So we reach this conclusion to pass the climatic Turing test is a sufficient and necessary condition for building a perfect climate model. Unfortunately, we now have computationally tractable approach to march toward this objective. That is adversarial learning. And here we are not using any random noise. We're just using the model as a latent. And this builds the connection between generative model and dynamical systems. And we can also analog this practice to human intelligence-based model diagnosis. Usually we hire several postdocs or PhDs to come up with hypotheses of where model is wrong. And we collect the data. We do weather hindcast. We do climate simulation and compare with the climatology in reality. We refine the hypothesis. But here we are using a Turing test to come up with where the model is potentially wrong. And we learn to disentangle dynamics and physics using this adversarial learning. And we channel this discriminators information to the bias corrector. So we correct the bias under some self-supervised constraints. So we usually come up, the human intelligence is used to constrain this GAN framework. And then it comes back to the kinematic Turing test. So it just channels everything in a flow. If we come, the benefit of streamlining the workflow is obvious. So previously when we were trying to build a car, it takes a long time, but now we have the workflow. It's much faster. And nowadays we can use machine intelligence to automate the iterative research cycle for refining GCMs. And we may go even a little bit step further. That is, in the GCM, we have the dynamic, we have the numerical solver for the geophysical fluid dynamics, and we have the parameterization. We update, we refine the dynamics, we refine the every few time steps, and we give output. But here, if we just replace everything like what they did for learning parameterization using this adversarial learning paradigm, we may just combine all the parameterization schemes into one big neural network. And then at the very end, the observed reality is indistinguishable from the simulated model world. We may come up with something called neural simulator. So this is a GAN solution. But I think we may have a game changer here. It's called denoising diffusion probabilistic model. Let's come back to this slide again. Before June of this year, you may say that you are doing novel machine learning research using GANs. But nowadays, people ask, why do we still care about GANs? Why do we still care about GANs? Because we now have a better solution. So when we are doing probability forecast, we ask a question, what is required? We need reliability and resolution. There is a huge literature talking about what a good probability forecast is. And what is required for a good generative model? It should give us good samples. It should give us good distribution coverage, exact likelihood estimation, quick sampling, training stability. Some of them GAN can meet, while some of them VE can meet, but none of them is perfect. And but these two communities, there is a culture gap between these two communities. So we ask, what is required for a good generative model that can support probabilistic climate forecast, or even more? So if we can have accurate estimation of high-dimensional PX, we can quantify what a climatology really means, not only the climatology mean, but the climatology distribution. And we can quantify the internal climate variability. We can quantify how extreme an extreme is. Also, if we can estimate this probability, we can better store our data. We don't need 30 petabytes of storage to store CMIP6, because we can link probability and information theory. And we can use it to benchmark predictability. And also we want a probability model to flexibly inject the control of, or control some conditions, like Y. Because if Y is a partial observation, we want to have PS given Y. Given this observation, what the initial state will look like. Or we can do probabilistic forecast. Given this prediction source, what's the future look like? Or we can do detection attribution. Given this external forcing, how this distribution shifts. And also we can do flexible domain adaptation if we can easily do like PX or PFX for model diagnosis. Because in different scenarios, like what we do before, comparing the climatology of reality and the model, or do climate change detection, compare different forcing scenarios, simulation, and see how they differ, how the distribution differ. And we may even like design better forcing scenarios for future MIPS. So what's the deficiency of VE and GAN? They always try to generate the object in one step, right? And we know that the world is iteratively generating because the laws apply themselves iteratively every few time steps, they update the state. Can we do iterative generative modeling? And we find the connection between generative model and stochastic differential equations. Assume we have the data, like the picture of the dogs, and we can design this forward stochastic differential equation, a dx of fxt dt plus jt dw. W is the Brownian motion. And if f is a fine transformation, we can transform the data to white noise. And we can go from here to each step analytically. And for each forward stochastic differential equation, we have a reverse stochastic equation, which allow us to get from noise back to data. And the only thing we need to estimate is the score function, which is the density, is the gradient of log probability. And how can we estimate this? Well, we can do score matching, which is a well-developed technique. And after we do score matching, we can estimate for each time step what this gradient loss function or gradient would look like. And we can use normal SDE solvers to inverse this process to get us from noise back to data. And we can view this process in an infinite steps VE perspective or score model perspective. Score is the gradient of log likelihood. We know that in doing probability modeling, we only need to have P integrated over this sample space to 1, which is a very strong regulation. But if you just look at its gradient, there is no constraint here, and the model becomes super flexible. And we can also see it from an Ito calculus perspective, which I illustrated here. And the good thing about this, let's first look at the process. We have the handwritten digit. We gradually inject white noise to give us the white noise here. And we can do the denoising by estimating this score function and reverse this SDE. And here we get the sampled result. And here are some results from the reality, from the original data, from VE, from GAN, and from the diffusion. And you may guess which is which. This is from VE. It's pretty blurry. This is from GAN. You can occasionally get really good results, but when you're trying to do interpolation in the latent space, you get something that is weird. And these two, you cannot tell which is reality, which comes from the diffusion model. And here is comparing their climatology. This is VE generated samples. If we try to classify their generated samples into the 10 categories, and here is the distribution. This is the raw sample. This is GAN. This is diffusion model. We want to recover the whole distribution here, rather than giving us some mode collapse or some inaccuracy estimation of the model coverage. And the other thing here is that this framework can allow us to easily inject the control of Y or sequentially inject the control of Y here. So with this, after we train this score-based model, and conditional probability distribution, we can easily turn it into a conditional distribution, which is what DALI 2 stable diffusion did nowadays. And here, if we look at how can we apply the diffusion model to do climate research, if we look at, I have a very grand proposal that I try to submit, and that is we can build the whole CMIP into a single diffusion model. We know that we have come through the 6 phases of CMIP, but originally we only have some very preliminary control experiments, very few models, very little data set. But now we have like 30 petabytes, and we have set up the experimental design deck, historical different future scenarios, and different MIPS targeting toward different processes. But the key consideration is that we don't have enough sampling of internal variability noise. Even we have a lot of RRPF. We have ubiquitous model systematic biases, and we do not sufficient sample future scenarios. Here we have 4 scenarios. Here we have 8. In CMIP 7, maybe we have 20. But I hope in CMIP 7 we can have infinite sample scenarios. So we need fast generation of model examples to sample internal variability noise. We need to learn where model different and where they differ from reality. we need to create representative mission scenarios. And so the diffusion model is kind of like a denoising autoencoder. It allows us to see that how the climatology, what the climatology is using a pure probabilistic language, and how to represent the interaction between different variables at different scales, and the results are pretty good regarding every aspect, except that it's a little bit slow to generate the samples, because nowadays we are trying to generate step by step instead from just pure noise to the results that we care about. So this is the framework. We try to maximize the log likelihood of something we care about, condition or something we think is important in different domains and in different models, in different scenarios. And these are all the things that I want to present today.
All right, thank you. Thank you so much for the great talk. So any questions? You can either raise your hand or type your question in the chat. Okay, so we have the first question from Dr. Jianlu.
宝强你好，我先问两个最简单的那个常识哈，我那个 make sure follow this. One is the latent space， 一般来说应该是降维的是吧？应该是 dimension 一定是比原始的 space 要小好多是吧？
对。
OK， 这反正很简单，我只是 clarify 一下。
但是这不是强制需求的。
我
就是说，
对，
你像这个。你像这 diffusion model， 它的 latent space 就是和原始的数据是一样大的。
我当时忘了说是你那个早期的那个 slide， 我不知道是哪个 number。那个另一个问题就是说是就是早期的那个你的 example， 你的得意之作，你是不是也是目的也是要 train 个 operator， 那个 M 是个 operator 是吧？这是个，
你是说
你这个方法是不是 operator based or purely statistical approach？ 应该是更早的那个 CGF 那个结果 CGF。
这个是 pure empirical 的。
pure empirical， 不是 operator based。OK， 这是我主要的问题。
对，那你是可以用那个 Fourier neural operator， 或者是其他的那种像就是像 Brown 他们提出的一些 operator。我这里其实强调的是这个 loss function 的设计。就是你是完全可以说我不用 CNN， 我用 transformer， 我用 swing transformer， 我用 Fourier neural operator， 或者是我用一些更其他的一些骨架的东西来支撑这个 paradigm。
OK， 行，我先问两个简单的就是 clarification 的问题，别的以后等他们问完我再接着问。
好的，谢谢张老师。
好的，谢谢。
好的，谢谢啊。接下来请陈刚老师提问。
你好，
汤老师。
对，非常有意思。我想问一下关于你做那个 diffusion model， 然后你那个讲到 diffusion model 那是有 time derivative， 但我理解其实都是一些 noise 或者 error 让它变得和真实的不一样，是吧？
就是你可以想象，如果是我们这边 F， 我们把它写成我们的动力的方程的话，我们这个过程，我们也可以加一个 Brown noise 进来，再加一个 Brownian motion 进来，我们是可以反过来解它的。这只不过是说，像我们之前解这些数值，
这个可以理解。我的问题其实就是说，比如说你现在是说给定在最右边那个图片，你要反推最左边那个图片，是吧？
对。
那比如说我们假设你是有一个 annual mean 或 seasonal mean 的数据，那数据你是说数据看上去是最右边那个图片，然后你想推一个真实的吗？还是说你那 noise 其实代表是 weather noise？ 可能是不同的解释，我只是想
就是你如果左边放的是 weather chart 的话，然后右边可以是 noise，然后可以说我们怎么样从 noise 生成这个 model 的 climatology， 这是最 最直接的一种应用。但是我觉得这种框架的话，它提供了一种把我们的动力写到 neural network 里面的一个框架。我们传统的一些物理认识的话，即使再复杂，它也只是几行方程，虽然解起来可能非常非常的复杂，但是它写起来就是几行方程，而且那个方程的系数，包括它的任何的项，都不会是一个特别长、特别复杂的一些东西，因为我们是非常非常简化的，我们人只能处理这些。
对，这个
但是你如果
完全
看下面这个方程的话，这个 delta x 它是一个非常巨大的 neural network， 而且在解的时候，每一小步你都要把它调进来，这就是为什么 sample 比较慢。但其实
这个我也可以理解，我就是主要是想问的是，比如说你这个如果只是图片的话，左边右边是同一时刻，但是我感觉你说是要用它做一个 forecast model，是要用来做积分的，是吗？
这个是你就像 Fourier neural operator 一样，我们可以说我们只放一个图片，我们也可以说放10天的这个天气图。就像现在这个模型，好多人用它来做 video generation，video 他们会生成5到10分钟的一个小电影，然后每分钟有24帧。
我知道，就你其实还是想用它做一个相当于做预报的，这个和你之前做那个 signal forecast 不一样，那个就是从1年到另一年，但这个呢就是相当于是你今年有的让你做积分。
对，我可以从现在积分到明年的每一天，我可以生成明年每一天。然后还有一点就是说，这个东西可以和 GAN 放在一起，就是 GAN 的话，相当于说我一步的做 discrimination， 那我现在用 different GAN， 我每一步加噪声之后，我再做 discrimination， 它就会效果就会非常的稳健。
你同时还要 learn F 吗 ？F 你是怎么 learn？
那就 GAN
F 是事先定的，F 是根据你的名字定的。
是 given，
像这个 forward 的这个 SDE 的话，所有的都是定的。然后你这个 x 不一样，那你的这个 delta PTX 就会不一样。你学的是反向的这个 gradient 项，然后学完了这个之后，你可以用常规的这个 SDE 的一个求解器，把这个从白噪声变到你任何想要的一个数据。
OK，F 知道的 OK。
那你其实现在做就是还是根据在 time step t。然后甚至可以根据 time step 0来 infer 那个 probability distribution 是吧？
对，如果 F 是一个 affine transformation 的话，那从 x0到这个是可以有一个解析解的，就是这个 distribution 和它这 distribution 的 dependency 是有一个解析解的。但是反过来的话，就是从信号到噪声是很简单了，你只要不断的模糊信号就好了。从噪声到信号需要你学这个 score function， 而且这个东西如果 F 不是 affine function 也有方法来解，所以我觉得这其实是一个非常重要的一个理论上的一个突破。
行，谢谢。我觉得这个倒是很有意思，可以把一些动力系统的东西加上统计的放在一起。
对，这个之前是从那个longevity dynamic， 就是朗之万动力那个东西来的。
好的，接下来有请吕江老师。
如果没人问，我再问一个比较 critical 的问题，就是说我可能是 rumor 哈，有人告诉我那个大家都是 celebrate 那个 ham 那个是吧，可以预报好多年那个 answer 的，好像有人说即使 ham 也没有 beat， 就是我们 mainstream 的 model。
我觉得是因为它。
就我的问题是，现在有任何的 evidence ever 这个 machine learning 这个整个 community beat 我们 traditional 的 community？ 假设我们是2个 team，OK， 竞争。
对，就是第一，它有2个非常重要的缺陷。第一，它是把所有的数据混到一起 train 了，它每一次 train 的结果都会不一样，数据是异质的，就 inhomogeneous。那这时候它混在一起， 那它到底学的是哪一个？它没有明确的标明知道你是学的哪一个模型里面的这个 M。第二，它如果它那样混的话，同时它又是用了一种监督学习的方式，它要的是 expectation of y given x， 它求的不是 py given x。那我们可以假设这样一个实验，比如说我们有100年的 NSO 的一个观测，然后我设计的实验是，你抽出来50年，你自己选定哪50年，然后你把你的技巧，你把你的 correlation 技巧告诉我，这个是，比如说我如果是能够标的我这种模型的话，那我就会选择 py given x 它的 variance 最小的50年，就是可预报性更强的50年，我来给我的这个汇报我的结果。就是它第一，它混淆了这个东西；第二，它没有给出概率预报。它没有给出概率预报的话，它就不会说更好。或者说它不够全面。
对，
我是觉得可以用那个 diffusion，在这种方法情况下可以做出更好的结果。然后如果是真的有您说的这种比赛的话，要和动力博士打比赛，比如说我们赌，我是愿意去赌的，因为我觉得如果给足够的数据，给足够的算力，给足够强大的算法，没有理由会比他差。
OK， 还是有希望的。我因为上次那个听他 Schneider 这个报告，他也说过，他说在他的眼里好像从来没有，就是说 machine learning 的新东西能够 beat 他的传统的 approach。这个
那是因为监督学习是绝对不行的。
OK， 反正 so far 好像大家还没有 achieve 这一点，你才说 OK，game changer 来了。
对，我觉得 diffusion 是一个 game changer。
OK， 对，这倒是非常 promising。那个 framework 我不知道哈，我感觉很像 LEM，except 那个算子那部分是非线性的，那是非线性的那种 LEM。
对，这个领域其实说真正火起来就是最近，然后理论上应用上的文章层出不穷。我觉得是一个非常大的一个金矿。我们领域目前还没有人真正在这个地方能做出东西。谷歌已经出产品了，但是他们论文还没有出来。就是用它来做天气预报，加上 FNO 加上这个东西来做天气预报，就是可以做概率的10天的预报。
对，
但是我印象是，其实像那种 fair operator， 其实也就只能做短期，时间一长都会 crash。然后我上听做报告说，其实在做这种计算的时候，就出现那种，其实做数值预报的时候，大家都知道的问题，就是比较小的 scale 就 noise 越来越大，然后就会出现最早期模式的问题，就是有一些小的 scale 的 noise 太多了。但有可能这个 diffusion 的这种办法，有可能能够去掉一些这种小的 noise 吧，我不知道。但是现在我知道那种就是用来做预报，基本上都不能持续特别长时间。
我觉得我们是应该放弃掉这种长期的确定性预报的一个想法。我们应该说，我们在不同的尺度上，我们应该既模拟信号又模拟噪声。这个信号可能是一些就是 low frequency 的东西给我们的，或者说在更长期的时候是气候变化的信号给我们的。但是我们对之前我们做 machine learning 一直没有对 noise 进行一个很好的模拟，或者说 noise 和 signal 之间的 interplay 进行一个很好的模拟。然后这两个需要很好的模拟的话，其实是需要我们这个 model 能够能够很灵活的把我们的这个 condition 给它注入进去的。然后之前的 GAN 和 CVE， 如果你串的话，你如果做串 conditional GAN、conditional VE 的话，你是没有办法明确我们的信号和噪声在你的结果当中到底是占一个什么样的权重的。而在这里，通过这个方式，你是可以明确的用一个参数来知道我信号加的多强，噪声加的多强，我的结果会怎么样子。然后我再和传统的这种叫做这个东西建立联系。就是 generative model 这个 community 现在注重于做 generative model， 它不注重做 conditional generative model， 直到今年，直到 diffusion model 出来，现在有一个专门的领域叫做 prompting， 就提示怎么样提示一个 AI agent， 让它做到我们想要做的事情。 然后所以我觉得这个 game changer 真的要来了。
对你刚才说那个 diffusion model，immediately 我马上想到的就是对我们气候里面，比如说特别中纬度大气动力学，对 to some extent 好多的东西是 noise forced。那现在是哪一部分是 noise， 哪一部分是吧？哪一部分是哪一部分？就可以说这个 de-ambiguation 这个关于这些东西我们不知道，现在不知道，也从来没听说过有个好的 tool 来做这个，现在真有可能。
对，
对，而且跟那个大气动力学结合起来，说不定很好。大气动力学里，我们可以非常明确的，可以自己 define 什么是 F， 是吧？QG 动力学，
对，
线性化的，还是半线性化的，还是2阶3阶线性化的，都可以人为将 knowledge 给它 inject 进来。
对，我觉得这种 physics informed machine learning 比在 log function 上加那个东西要高级得多。
对，我觉得那个是很好，我们动力学 community 也比较喜欢。
对。因为 F 只是在这里，然后在这里，它和这个 neural network 是完全解耦的，而 GT 只是控制你的 noise， 它在这里。
对。OK。
谢谢啊，大家有什么问题还可以继续提问。我先把这个录制结束一下。